Hello students, we are going to discuss about a practical integrator circuit. In case of practical integrator circuit, one of the addition we are going to make in ideal integrator. In case of ideal integrator, this resistor element is not present. But what happens if this resistor element is not present at low frequencies? The overall impedance in a feedback path will becomes infinity as capacitive element will become open, and the output of amplifier or the output of integrator goes to saturation. So to avoid this problem, we are connecting resistor element in a feedback path in parallel with the capacitor. And now what happens, even if at low frequencies capacitor is element, there will be resistive element in a picture, and at low frequencies the gain of circuit will become Rf by R1 as the input is connected to inverting terminal, it is minus Rf by R1. So at low frequencies practical integrator behaves as an inverting amplifier, and as the frequency goes on increasing, the square wave gets if you applied input square wave, then square wave gets converted into triangular wave. The formula for the design case are the design frequency FB is equal to 1 upon 2 pi R1 CF, FB is equal to 10 times of FA, and FA is equal to 1 upon 2 pi RF CF. FB is a frequency at which magnitude plot reaches to 0 dB value, means gain goes on decreasing and it reaches to 0 dB. FA is a frequency at which magnitude or gain magnitude plot has a value 3 dB below the maximum gain. The design which we have considered is FB is equal to 15.9 kilowatts, FA is equal to 1, that is FA is 10 times less, so FA is equal to 1.59 kilowatts. Consider CF we have connected as a 0.1 microfarad, and then by equations RF is equal to 10 kilo ohm and R1 is equal to 1 kilo ohm. Then offset minimizing resistor connected between pin number 3 and ground is 1 kilo ohm, which is a parallel combination of 10 kilo ohm and 1 kilo ohm. This is the basic design circuitry of our practical differentiator circuit. The measurements which we are going to take are input frequency. We are going to vary the frequency from 100 Hz. As we have discussed that at low frequencies our practical integrator behaves as an inverting amplifier, and by design the gain is 10. This is the output voltage for increase in input frequency. Then second one is output voltage. The third column is a gain, that is output voltage upon input voltage, and the fourth column is a 20 log of V0 upon Vin, that is we are calculating gain in baby. We are going to apply input voltage 1 volt peak to peak square wave input signal. This is the basic about readings we are going to take. This is the response of a differentiator. As I mentioned, for a basic integrator, when resistive element is not present in a feedback path, gain is very high and the output goes to saturation. So this is the response for basic differentiator. When we have basic integrator, when we have connected capacitive element and resistive element in a feedback path, the dotted line shows the response for ideal integrator circuit, and when we are going to take the measurement, this type of response we are getting for a practical integrator circuit. So in this case for integrator, we are going to observe the response, or we will get the response like this. This is the practical integrator response. This is the frequency FB at which gain drops to 0 dB, and this is the frequency FA at which this magnitude plot has a 3 dB below the maximum gain. So these are the FA and FB frequencies. We will check the values now practically. The initial we are going to use this function generator. By using this function generator, we have selected 1 volt peak to peak and a square wave input signal. By using this knob, we are going to vary the frequency. These are the knobs for range selection, and by using this knob, we are obtaining the 20 dB attenuation of the signal. For operational amplifier 741, we need a dual power supply. So we have connected plus from the dual power supply to pin number 7, minus from the dual power supply to 4, and a common terminal we have connected to ground. And we are going to observe the output on a digital storage oscilloscope. Right now the yellow waveform shows the input signal. We have applied 1 volt peak to peak square wave input signal, and the blue shows the output signal. As I mentioned, at low frequencies the output is a inverting of the input signal. So if you see over here, the output is also a square wave and the output is 10 volt. We have selected resistive element RF 10 kilo ohm and R1 1 kilo ohm. So gain is 10 and it is a inverting result we are getting. As now, so initially at low frequencies, as we have mentioned, the circuit behaves as an inverting amplifier. Practical integrator behaves as an inverting amplifier. If we will select the next frequency now to 500 Hz. Now if you see the waveform, first thing is amplitude goes on decreasing for the output signal, as well as the shape of waveform goes on changing, means it is tending towards a triangular wave now. Means our circuit is reaching in a integration mode. This result we are getting at a 500 Hz. If we will take the next measurement at 1 kHz, now you will see the waveforms properly. Now this blue waveform is moving as a triangular wave and we have selected a frequency 1 kHz. So at 1 kHz the output is 9.6 volts. I have selected the input frequency as 1.6 kHz and at this we are getting around 8.6 volts. As still we go on increasing the frequency, if you see the blue waveform is a triangular wave and the output continuously decreases. As we go on increasing the frequency, now let us focus on this waveform. I will change the frequency to 5 kHz. And see the waveform, triangular waveform, you can see clearly the output voltage goes on decreasing continuously. I will take the frequency to 10 kHz now. At 10 kHz the output is 2.56, means still we have not achieved the frequency FB. Now still I am going to increase the frequency. At around 18 kHz we are getting 1.32 volts, and as we still go on increasing, if you see now the amplitude is reaching towards 1 volt. Just concentrate on this waveform, we will take the measurement. See, at around 20 kHz we are getting the output voltage is equal to 1 volt, means the amplitude of blue waveform, that is triangular in color, is 1 volt peak to peak. The integration takes place. We have achieved the input waveform here, input waveform in yellow color and blue waveform as the output signal. Here the output waveform, that is blue, is a triangular, and here at 20 kHz the value is 1 volt, means FB we have obtained. We have designed FB as a 16 kHz, 15.9 kHz, and practically we are getting 20 kHz. This is the limitation because of the limitation of the instrument we are going to use, or the tolerance of the components which we are going to use. Means the integration of input signal we have achieved, square wave signal we applied, and integration of square wave we are getting as a triangular wave at the output side. So the integration is obtained properly as per the design we are considering. Let us focus on the components which we have connected, or the setup which we have considered on a breadboard. At the input side we have connected the resistive element here 1 kilo ohm. In between feedback path, that is in pin number 2 and 6, we have connected a resistive element and a capacitive element. The resistor selected is 10 kilo ohm, and between pin number 3 and ground we have connected 1 kilo ohm resistor, that is offset minimizing resistor, and we have considered the output is taken from pin number 6. That is the basic pin configuration of operational amplifier 741. Hence the integration of signal is obtained successfully. Thank you.